So now let's put together everything that we learned about the least squares regression line for a particular problem. And in so doing, we'll learn what it means to be a least squares regression and why that's the best fit. So we found in section 4.1 that there's a linear relationship, more or less, between the fertility rates and the life expectancies for the 201 countries of 1962. And here they are. So the fertility rate is the x, remember, the life expectancy is the y, and we have this trend line going down the middle of our graph that we've seen the scatter plot before, but now we have this line attached to it. Okay, so we are supposed to explain the meaning of the slope of the line in the context of the situation. So let's start with what is the slope of the line. The slope is negative 4.6711. The slope is always multiplied by the x value. So for my purposes, I think it's best to kind of write the 1 in the denominator because it helps to remind us that we have to explain this ratio. And then not only is it nice to put the number, negative 4.6711 over 1, but it's super helpful to put the units in. So the unit for the y variable was years, and the unit for the x variable was births per woman. And that helps remind us what we're talking about. We're saying, look, if the births per woman increases by 1, then the years, the life expectancy, is expected to go down by 4.6711 years. To keep with the color coding we used before, the x I will do in red here. So the 1 is in red. So that's this phrase right here explains the x equals 1. So if a country's increase their fertility rate by 1 birth per woman, then we would expect that country's life expectancy, that's the y variable right here, to go down by 4.6711 years. All right, now explain why the y-intercept does not make sense in this situation. Well, let me first write up what the y-intercept is. If we look back at the problem right here, remember that the x is always, the slope is always multiplied by the x. And the other number sitting out there on its own is always the y-intercept number. There, I just made a note of that part right here because a lot of students forget which one's which. So the slope is the one that's multiplied by the x. So that means that our y-intercept is 0, 81.51. But think about what that is. That's x, which is 0 for your x value. So that's 0 births per woman. And that's y, which is years. Right? That's the unit for the x, and that's the unit for the y. So this would be the y-intercept, where that part is the x value, that part's the y value. Now the reason this doesn't make any sense is that you'd have to have a country be able to have 0 births per woman, which means you'd be living in the movie Children of Men with Clive Owen, because that's sci-fi stuff. You can't have a country that has no births per woman, no pregnancies whatsoever in the entire country. That's completely unrealistic. So that would be a sci-fi movie premise. That is not real life. It's impossible for a country to have no births per woman at all. And honestly, usually it's the x value that doesn't really make a lot of sense in the situation. So if you're looking for why the y-intercept doesn't make sense, look to the x value. Usually there's a good reason. It might be the y value too. Sometimes they both happen, or sometimes just the y, but a lot of times it's the x value. Okay, so the United States had a life expectancy of 70.21 years in 1962. We're going to calculate the expected fertility rate. Now we actually know the fertility rate because it's in a table several pages back, but we're actually going to make a calculation here. Now you'll notice I'm giving the life expectancy. So the life expectancy is the y value. So I'm giving a y that is 70.21 years. And then I ask us to find the expected fertility rate, but fertility rate is births per woman. In other words, I'm giving you math teacher code, right? The math teacher code is, hey, the y is this, find me the x. Now this is one of those rare instances in this class where we're actually going to do a little algebra. I know it's a little scary, and solve for x. Just real quick to note that this is actually a y hat value. It's a hat value because it's actually on the line, not the dots. The dots y values are y's. So each of these dots has an x and a y value. The y hat is the trend line, the average, if you will, of the x and y's. Just a little housekeeping note there. All right, so I'm going to set the equation, which is negative 4.6711 x plus 81.51. I'm going to set that equal to the y value, which was 70.21. Now the first thing we're going to do to solve this for x, because that's what we want to do, is to subtract that 81.51 from both sides of the equation. So I'm going to take 70.21. I'm going to subtract 81.51 from both sides. Over here on the right, it's going to cancel out. Over here on the left, it's going to turn into a negative 11.3. There, just to show the work, I kind of typed it in there. So minus 81.51 to the left and the right side of the equation. So that leaves me negative 11.3 equals negative 4.6711 times x. There's no times dot in there, but it is a times dot. We're just too lazy to write it. So now we're going to divide both sides by that negative 4.6711 because the way to undo a multiplication is division. So we divide both sides by negative 4.6711. So let me grab my calculator. I just hit the division symbol and it takes the last answer, which was negative 11.3, and I divide by negative 4.6711, enter. And I get that x is approximately 2.419. And of course that would be, well, let me make it 4.2. And that would be births per woman because it's an x value. And the x variable was fertility rate. So it would be births per woman. There we have it. All right, so let me just go back up to the graph real quickly and just kind of show you what we just did. Oops, if I can do this without moving my lines 1 second. So this problem's a little weird because we set the y value set in stone. So if you remember, the actual US values right here over on the right hand side, and then we set the y value at 70.21. We kind of work our way over to the line and figure out, hey, what x value did we think that would be? So our actual US value is somewhere in the 3.4 range, right? It's about halfway between 3 and 4. But where we predicted it would be was x equals 2.42, what we just found, which is significantly over because all I'm doing is drawing a line from the point over to the diagonal trend line. So I'm saying, hey, my y value's set. Let me cross over here and see where it intersects with the graph, and it intersects at 2.42. That's visually what you're doing. All right, now this is interesting, but we don't do this way very often. We're not often moving from left to right on these graphs. We're usually moving up and down, which is what the next one's going to show us. So a country in 1962 had a fertility rate of 4.54 births per woman. Using the linear equation given on the graph, what would we expect that country's life expectancy rate to be? Okay, so instead of giving you the y value, I'm giving you an x value here. So I'm saying that x is 4.54 and asking what that country's life expectancy would be expected to be. So this is sort of the opposite problem from last time. Last time I gave the y and was looking for an x value. This time I'm giving an x value and I'm looking for a y value. Okay, so it's actually simpler algebra than the last one, to be honest. All we're going to have to do is substitute that value of x into our linear trend line equation. So let me grab the linear trend line real quick. So this is the equation, and instead of putting x, we're going to put in a substituted value of 4.54. So let me go grab the calculator and just type this all at once. Now remember, when you do this, use the negative symbol, which is down here next to the enter. Don't use the subtraction symbol because it won't know what you want to do. So negative 4.6711 times 4.54 plus 81.51. Enter. And we get 60.3 roughly. So let me put that down. All right, so that's it. That's all there is to it. I mean, it's very simple. Okay, but there actually was a country that had this as their birth rate. It was the country of Gabon, which is in sub-Saharan Africa. In 1962, Gabon had a birth rate of 4.54 children per woman, and it had a life expectancy, I'm sorry to say, of only 39.56 years. I believe they were in the middle of a civil war at that time, which tends to lower life expectancy rate, obviously. So we're going to compute, draw, and label the residual, i.e. the error on the graph, because we're obviously not correct. We are making a guess with the 60.31 to where it should be. So as we do this, I'm going to show you what a residual is. So let me go back to the graph real quick. Now Gabon's actual value, I chose Gabon because it was so out here kind of on its own. Gabon is this dot right down here. That's where it actually was. So that's a y value. The y value was truly real life in observation. We observed it to be 39.56. The prediction we just made was higher than that. It was 60.21, which is up, straight up. So if I draw a line vertically straight from the pink dot right up, and intersect the line, that would be my prediction that we just made. There we have it. So Gabon's predicted y hat. So the y hat is the predictions. The hats are the ones that are on the line, and the y values are the ones that are the dots. So the predicted y hat, which is straight up from that pink dot, so a vertical line straight up, that is 60.3 years. Is what we just found. The residual is the error. It's how off these two are. How far apart are they? So what we're looking for is the vertical distance between those two dots. So we need to be able to find this vertical distance between the 2 points right there. And the way to do that is to use the formula right here, which is that the error is the residual, which is the observed y value minus the predicted y hat value. In other words, it's what actually occurred in real life minus what didn't occur, or what you predicted occurred. So what actually happened minus your prediction from the model, from the trend line. Let's put it that way. So I put that in there. The actual value y minus the line y hat, the thing that we get from the trend line. I guess I could say trend line. Trend line. Okay, so if that's the case, then our residual will be, for Gabon, will be the y minus the y hat. Now the y was from reality, which was really 39.56, minus our prediction, which was 60.3. Now you'll notice that the units for these are years, right? It has the same unit as the y value for our data set. So if I take 39.56 and I subtract away 60.3, I get negative 20.74. So that would be my residual, negative 20.74 years. It has the same unit as the y values for my data set. Which means if I go back to the graph and I look at the vertical distance right there, that residual is negative 20.74 years. Notice it's all in years. The blue dot's y values in years, because I'm only concerned about the y values. They have the same x values. And then the pink dot's y value is 39.56 years, and the residual is the vertical distance between the two, which is negative 20.74 years. That's a sign that our model overestimated what this value was going to be, because the estimate is the aqua dot right here, and that is higher than what it actually was. So our estimate is higher. If you have a negative residual, it means you're an overestimate. The line is above where the value actually will be. Now keep in mind, this line overestimates half the dots and underestimates the other half of the dots. That's what makes it the line of best fit, that it kind of balances out the dots above and the dots below. As a matter of fact, that's exactly what it means to be a least squares regression. It's that it balances all these residuals, and that the residuals between the dots above and the dots below all balance each other out. Now, before we get into any more about residuals, real quickly, what does this reveal for us about Gabon back in 1962? Well, Gabon was not doing very well, right? Because the life expectancy in that country at that time was way below what we would have expected. All right, so to interpret this, we would say Gabon was not doing very well, as the life expectancy in 1962 was far below what we would have expected. In other words, people were dying much younger than we would expect. And another little note, it's kind of a minor point. This is not really an interpretation, but just something to notice, that our model overestimated. We actually have this prediction kind of on the left, where the prediction was higher than the observed value. If you have the opposite, if you have the prediction, the real life observed value is higher, so the pink one is higher than the prediction, then the model underestimated. That's not really an interpretation, it's just something to make a note of. The interpretation part is here, where you kind of put it into the context of the problem and figure out how well this thing was doing. One other thing to really note, a couple things, that of course the residuals have the same units as the y values, so in this case it was years everywhere. The least squares regression line is the model that makes the residuals the smallest they can possibly be for all the data points. What I said before, it balances the high and the low errors, and that trend line that you see is the best one. And the size of the residual can tell you how well the model's fitting your situation. So if it has smaller residuals, that's generally a better fit. The closer the dots are to the line, in other words, the better. And again, one last time, if you have a negative residual, it means your observed point was below your prediction, so the model overestimated because your observation was below. If your real life observation was higher, then the model underestimated because your prediction is below. So if the prediction is lower, it's underestimated. If the prediction is higher, it's overestimated. But again, in most data sets, they're going to balance out. About half the points will be under and half the points will be over.